Hello everyone. So let's try to recap what we have discussed in the previous lecture. So we have derived the dispersion relation for 1D linear chain of atoms, or what I can say is uh, a linear monoatomic lattice. So, and we have seen the limiting cases for such as in the long wavelength limit, where this lambda is very larger than the lattice spacing. We have seen that this sine ka by 2 was nearly equal to ka by 2. So therefore our dispersion relation omega was equal to vs times k, and we have seen that the phase velocity and group velocity were equal, and they were equal to the sound velocity in the lattice. While at the zone boundary, where this k value was pi by a, the dispersion relation gave the group velocity to be 0 and the phase velocity to be around 2 vs by pi. And here also you can see that when at the zone boundary, this vibrations, they form a standing wave. Standing wave pattern. So where all these neighboring atoms, they move opposite to each other. So if this atom is moving upwards, so the next neighboring will move downwards, and next neighboring will move upwards. So in this way, it forms a standing wave. Also, we have seen that this zone boundary, which is k equal to pi by a, so this is equivalent to the Bragg's reflection condition equal to lambda equal to 2d. So therefore this zone boundary acts as a Bragg reflector. So this much we have done for monoatomic lattice. Now let's try to derive the similar sort of dispersion relation for a diatomic lattice. So now let's consider the vibration of 1D diatomic lattice. So now consider a 1D linear primitive lattice where the basis consists of two atoms of mass m and capital M. So these masses are placed alternatively along the x-axis with interatomic distance as a. So we can give a numbering to these atoms as, let's say, this small mass, it is at 2n. So this is at 2n plus 1, 2n plus 2, and similarly backwards, so 2n minus 1 and 2n minus 2. So this is a state of equilibrium. Now at the state of displacement, each of these atoms, they are slightly displaced from their mean position. So let's call the displacement by 2nth atom as u2n, and similarly for 2n plus 1th atom, so 2n plus 1, u2n plus 1, and similarly for others. Now using the similar assumptions which we used for monoatomic case, we can obtain the equation of motion for these atoms. So the force acting on the lighter mass, that is which is placed at 2n position, so that will be equal to mass times the acceleration, and that will be given by the Hooke's law as beta u2n plus 1 plus u2n minus 1 minus 2 times u2n, where this beta is the spring constant of these springs, basically which represents the interaction between the two atoms. So this is the equation of motion for the smaller mass atom, and similarly we can get a similar equation for the atom which is placed at 2n plus 1 position. So this is a heavier mass. So for that also we can make the equation of motion as capital M d square u 2n plus 1 divided by t square So that will be equal to beta u 2n plus 2 plus u 2n minus 2 times u 2n plus 1. So you can obtain equation 2 from equation 1 by just substituting in place of 2n, you can substitute for 2n plus 1. So we are seeking the traveling solution of the type u2n equal to a exponential iota omega t minus 2k and a, where this 2 and a, it is representing the position of nth atom, and the solution is a plane wave type solution. And similarly you can get the solution for u 2n plus 1 as b e raised to power iota omega t minus k 2n plus 1. Notice here that I have assumed the amplitude of these two solutions to be different for this vibration of small mass and the bigger mass, while I have assumed that the vibration frequency of these both types of atoms to be same, because the both types of atoms participate in the same wave motion, while the amplitudes A and B may be different because of different masses. So similarly we can write for u 2n minus 1 as b e raised to power iota omega t minus k 2n minus 1, and for u 2n plus 2 as a e raised to power iota omega t minus k 2n plus 2. Now let's try to write these solutions in terms of u2n, so that this u2n plus 1 will become b divided by a, and then I can write a e raised to power iota omega t minus 2k and a. So there will be one a also here missing. So this u2n plus 1 becomes this times exponential iota minus ka. So this will become b by a u2n and then e raised to power minus iota ka, and similarly this u2n minus 1 will become b by a u2n e raised to power iota ka, and this u2n plus 2 will become u2n e raised to power iota 2k with a negative sign. So let's try to substitute all these solutions in the differential equation. So we will get from equation 1 m, and then the double time derivative of u2n will give me iota omega raised to power 2 times u2n, and that will be equal to beta, and u2n plus 1 I can write as b by a u2n e raised to power minus iota ka, then plus u2n minus 1 I can write as b by a u2n e raised to power iota ka, and then minus 2 u2n. So I can simplify this by just cancelling u2n from both sides. So what I will get is small m minus omega square will be equal to beta b by a, and then this will become a cos function, so that will be 2 cos k minus 2, or I can write this in terms of these amplitudes as 2 beta minus omega square small m a minus 2 beta cos ka times amplitude b equal to 0. I just rearranged so that these amplitudes I can write separately. So this becomes my equation number 3. And similarly, I can write this equation of motion for this capital M mass. So that will become capital M times iota omega square, then u 2n plus 1 will be equal to beta. I can write this u 2n plus 2 in terms of u 2n plus 1 as a divided by b, and then I can write b e raised to power iota omega t minus k 2n plus 1 right, a separately, then e raised to power there is one negative iota ka left, so that will be this. So here I can write a by b u 2n plus 1 times e raised to power minus iota ka, and then similarly I can write for this u 2n that will be a divided by b u 2n plus 1 times e raised to power plus iota ka, and then this 2 times u 2n plus 1. So now I can simplify this by just cancelling out this un 2n plus 1 on both sides. So what I will get is minus capital M omega square will be equal to, and I can take common out this b from denominator as, so this becomes beta a common out, and then this will form again cos, so that will be 2 cos ka minus 2b. So now I can rearrange this equation to get in the terms of a and b separately, so that will become minus 2 beta cos ka with amplitude a, and then plus 2 beta minus omega square capital M b equal to 0. This becomes my equation number 4. So equation 3 and 4 represents a system of linear equations in two variables, that is amplitude a and amplitude b. So this set of this homogeneous linear equation can give me non-zero solutions if and only if the determinant made by the coefficients will be equal to 0. So if this determinant is 0, then only there will be a non-zero solution for a and b. So let's try to calculate the determinant for this. Then we will get as 2 beta minus omega square small m, then 2 beta minus omega square capital M minus 4 beta square cos square ka. So that should be 0 to give a non-zero solution for a and b. And we can simplify this by just opening this bracket. So what we will get is 4 beta square minus 2 beta omega square capital M, and then similar for minus 2 omega square small m. So I can write it as small m plus capital M, and then this and this will become plus omega raised to power 4 small m capital M minus 4 beta square cos square ka equal to 0. Let's try to simplify this equation. So here we have 4 beta square common in this first and last term, so that will become 1 minus cos square ka, so that will be sin square ka. So we can write 4 beta square sin square ka, then minus 2 beta omega square capital M plus small m plus omega raised to power 4 small m capital M equal to 0. So let's divide this equation by small m capital M. So what we will get is omega raised to power 4 minus 2 beta capital M small m divided by small m capital M omega square plus 4 beta square divided by small m capital M sine square Ka equal to 0. So this becomes the quadratic equation in omega square, and there will be two solutions for omega square, and they will be omega square equal to beta 1 divided by m plus 1 divided by capital M, and then plus minus beta under root of 1 divided by small m plus 1 divided by capital M square minus 4 sine square Ka divided by small m and capital M. So this is the solution for frequency. Note here that for omega values to be positive, we have two values of omega plus and omega minus, which you can get from this equation by putting plus or minus at a time. So we have two branches, that is omega plus and omega minus branches, and these two branches represents a different type of dispersion curves. So let's see what this dispersion curves looks like. So this image represents the dispersion curve for a linear diatomic lattice. So where this lower frequency, which is given by this black curve, it is representing frequencies omega minus, and this red one, they are representing omega plus. This omega plus frequency branch is known as optical branch, whereas this lower branch with lower frequency is known as acoustical branch. So therefore the allowed frequency range of propagation, it is split into two different branches. One is optical, other one is acoustical. The upper one is known as optical branch, whereas this lower one is known as acoustical branch. And if you notice here that this acoustical branch, it is resembling the dispersion relation for the monatomic lattice also, whereas this optical branch, it is represent an entirely different type of dispersion or entirely different type of wave motion. Also note that there exists a band of frequencies in between these two branches, for which the wave-like solutions of periodic wave, it is not possible. So this means that it is not possible to excite vibrations in a lattice at frequencies which lie inside this band. This is known as forbidden band. And the width of this band, it depends on the mass ratio of the two atoms. So capital M divided by small m. So larger will be the band gap if larger is this ratio. Also notice here that the existence of this forbidden band is a characteristic features of diatomic lattice only. You don't see such a kind of forbidden band in case of a monoatomic lattice. Now let's see the limiting case of optical branch. So for optical branch, the dispersion relation was given by with a plus sign in between the two terms. So let's see the limiting case. So case 1, when this k is tending to 0. So in that case, sine Ka is very small, so that I can approximate it as 0. So in that case, this omega plus square will become beta 1 divided by small m plus 1 divided by capital M, and then from here this term is 0, so only this term will remain. So that will be beta 1 divided by small m plus 1 divided by capital M, and this will be equal to twice of beta 1 divided by small m plus 1 divided by capital M. This means that omega plus will be equal to under root of 2 beta 1 divided by small m plus 1 divided by capital M at k equal to 0. So this means that this is the value at k equal to 0 for optical branch. So this means that the peak value here, its value is under root of 2 beta 1 divided by small m plus 1 divided by capital M. Now let's try to find this the value of omega plus at the zone boundaries. Case 2 will be when k tending to pi divided by 2a. Notice here that in case of monatomic lattice, here it was pi by a, but since the lattice here contains 2 atoms, so this means that the zone boundary now will be at pi divided by 2a, and sin ka value will be 1 at pi divided by 2a. So therefore omega plus square will become beta 1 divided by small m plus 1 divided by capital M plus, and this will be beta under root of 1 divided by small m plus 1 divided by capital M whole square minus 4 small m and capital M. So this is nothing but 1 divided by small m minus 1 divided by small capital M whole square. So our value of optical branch frequency at the zone boundary will become beta 1 divided by small m plus 1 divided by capital M, and then plus beta 1 divided by small m minus 1 divided by capital M, and then this term will get cancelled, so this will become 2 beta divided by small m. So this means that the value of optical branch at the zone boundary, its value is under root of 2 beta divided by small m. So the lower part of this optical branch, its value is depending on small m. Now similarly we can also find the value of acoustical branch at the k equal to 0 and at the zone boundary. So for case 1, when k is tending to 0, we are assuming that this value of sin k, it is approaching to ka. So this value is itself very small. Here we are not assuming it to be 0 so that we can get a meaningful value here. So this omega square minus will become beta 1 divided by small m plus 1 divided by capital M minus beta 1 divided by small m plus 1 divided by capital M square minus 4 k square a square divided by small m and capital M. Now let's take this first term common out. So this becomes 1 minus beta is common out, so this will become 1 minus 4 k square a square divided by small m capital M, and then here it will be small m capital M whole square divided by small m plus capital M whole square. So this small m and capital M, this can cancel out here, and if you notice here, this term is very small than 1. So therefore we can use binomial expansion to simplify this. So what we will get is 1 divided by small m and 1 divided by capital M, 1 minus half into 4 k square a square and then small m and capital M divided by small m plus capital M whole square as the approximate value. So this will become beta 1 divided by small m plus 1 divided by capital M, and then once this 1 cancels out this 1, so here it will be 2 k square a square small m capital M divided by small m plus capital M whole square. Or this can be simplified, this first term is simplified to get small m plus capital M divided by small m capital M, and then 2 k square a square small m capital M. Here we have a small m plus capital M whole square, so this term will cancel out and this will cancel out this. So what we will left with omega minus at k tending to 0 as ka underscore 2 beta divided by small m plus capital M. So this is the value of acoustical branch value at the zone at k equal to 0, k tending to 0. Now the second and last case, the value of acoustical branch at zone boundary, that is pi divided by 2a. So if we substitute this, then the sine ka value will be equal to 1. So in that case this will be 1, and what we left with is omega square minus equal to beta 1 divided by small m plus 1 divided by capital M, then minus beta underscore 1 divided by small m plus 1 divided by capital M whole square minus 4 divided by small m and capital M, and again this will be 1 divided by small m minus 1 divided by capital M whole square. So this omega minus will become beta 1 divided by small m plus 1 divided by capital M minus beta 1 divided by small m minus 1 divided by capital M. So from here this first term will get cancelled, and what we left with is 2 beta divided by capital M. Therefore omega, the value of acoustical branch frequency at the zone boundary will be 2 beta divided by capital M underscore. So this is the value at the zone boundary here. So this value is underscore 2 beta divided by capital M. Now we will investigate the physical difference between the vibrations represented by optical and acoustical branches, and I will also simulate that results, and we will determine what is the origin of these names of these branches. So for optical branch, we have derived the relation between the amplitudes earlier here. So these were the we formed a matrix here. So we will be using this equation 3 and equation 4. So here we got these two equations which relates the two amplitudes A and B of the two masses small m and capital M. So for this optical branch, as k tending to 0, so basically towards the origin, we can so for optical branch, if you remember, we have approximated the value of cos Ka to be approximately equal to 1. So therefore these equation 3 and 4 will give me minus omega square small m then capital A, then that will be equal to, this will be 1, so that will become 2 beta B minus 2 beta A, or I can write omega square divided by 2 beta equal to A minus B divided by small m capital A. And similarly here in this equation 4, I can substitute cos Ka equal to 1, so this will become minus omega square capital M B equal to 2 beta A minus 2 beta capital B, or this omega square divided by 2 beta will be equal to minus of a minus b divided by capital M and then b. So here we got these two relations. Now what we can do here is we just divide this equation 5 with 6. So what we'll get here 1 equal to minus capital M b divided by small m a, or I can write capital A divided by capital B equal to minus capital M divided by capital M. So this is the relation which represents the amplitudes, the ratio of amplitudes, which is equal to the ratio of masses. So if you remember, this A was the amplitude of small mass m, and this B was amplitude of capital mass M. So the amplitudes are reciprocal to its mass. Also, if you see here, there is a negative sign. So this represents a phase change of pi. So these amplitudes A and B, they are related by a phase change of pi. So this means that if the small mass m, it is going upwards, so the capital mass, this big mass capital M, it will go down. So here in the simulation you can see the optical branch, so that is the upper one, as Ka tending to 0. So here or here, so here if you see, this forms a wave. Now let's try to analyze this particular wave. So I'm stopping this particular wave. So here you can see that this red dot, it is representing the bigger mass, so that is mass m2 or capital M, and this black dot, it is representing smaller mass, small m. So this is representing optical mode with Ka tending to 0. So this is the wave for optical mode as Ka tending to 0. So here you can see that this it is the 0th line. So here amplitude is 0. So and beyond this, if this smaller mass m, it is going downwards, so its neighboring atom, it is going upwards, and then again its next neighboring is going in the opposite direction and upwards. So basically if you see the neighboring atoms, there is a phase change of pi, and the amplitude of these atoms, so basically it is proportional, inversely proportional to the ratio of masses, so that the center of mass of the unit cell remains unchanged. So if you remember, the unit cell in this diatomic lattice is of length 2a. So here if you see the center of mass, it is at this 0th line. It is always at the 0th line. Here you can see in this case also, from here to here, it will be such that the amplitudes will be such that the center of mass will be in the 0th line, so that the center of mass will remain unchanged, and such mode is known as the optical mode. Also, if you see here in this equation, so even if small m is equal to capital M, then also the ratio of amplitudes will be -1. So this means that this phase change of pi will always be there, so even if the masses are equal. So I will show you this in the simulation also. So here I have made the masses of these two atoms to be equal. So here you can see that if this black one is going upwards, so the red one is going opposite to that, and in this way the center of mass will always be at the 0th line, so that there will be no net displacement of the center of mass. So for acoustical branch, again consider these two equations, so the equation 3 and 4, but here the significant term in the cos Ka expansion for Ka tending to 0, so the significant terms will be 1 minus k square a square divided by 2. So we will substitute this and we will solve this equation 3 and 4, and also we will use that for acoustical branch the value of omega square is equal to beta divided by small m and plus capital M k square a square. So this implies that omega minus, as Ka tending to 0, was equal to Ka underscore 2 beta divided by small m plus capital M. So we will use these values and substitute here in this equation 3 and 4. So what we will get is minus omega square small m capital A. So here it is. So that will be equal to 2 beta B, and the value of cos ka in this approximation is equal to 1 minus k square A square divided by 2, and here this minus 2 beta A. And also if you substitute in this equation 4, then you will get minus omega square capital MB is equal to 2 beta A, then the value of cos ka 1 minus k square A square divided by 2 minus 2 beta B. So this is equation 7 and 8. And what we can do, we can add this equation 7 and 8. So what we will get is minus omega square MA plus capital MB is equal to, so basically these terms will get cancelled with this particular thing. So what we will left is minus k square A square beta A plus B. Now here we will substitute the value of omega square from here. So what we will get is minus k square A square, then 2 beta divided by small m plus capital M, small m capital A plus capital M B is equal to minus k square A square beta A plus B, right? And we can simplify this. Beta cancels out from here, and then k square A square, so that this 2 MA plus capital MB is equal to small m plus capital M and then A plus B. Now you can open this two brackets, so you will get small m capital A plus capital MB is equal to capital MA plus small mb. Now since we need the ratio of the amplitudes, so collect the amplitudes on each side, so that this will become A small m minus capital M, and that will be equal to B small m and then minus capital M. So this term will get cancelled here. So this implies that A divided by B is equal to 1. So this implies that the two amplitudes will always be in phase with each other. So this means that if the smaller mass is moving upwards, so the capital mass will also follow in the same direction, and it is a very independent of the value of their masses, and these amplitudes will be same for both masses. So this implies that, so if the and the next deriving will also be moving in the upward direction, so this means that the center of mass, so basically there will be a center of mass and there will be a motion of the center of mass also. So here you can see that for when the masses of two masses are equal, so this forms a wave where the neighboring masses, they are moving in the same direction, right? So there is no phase change. Also we can see if the masses are different, then also they are moving in the same direction, right? The only effect of the change of mass, the ratio of mass, is coming to this forbidden bandwidth, so or forbidden band gap. So the value of the forbidden band gap, it is increasing if I am increasing the ratio of the masses, right? So therefore we conclude that in case of optical modes or optical case, the neighboring atoms they move in opposite directions, where in the case of this acoustical mode, the two atoms, the neighboring atoms, they move in the same direction. And this is the characteristic feature of the optical and acoustical branches, and this holds for other values of k as well. Now let's see what happens when the capital mass m, it is changing, it is very large compared to the smaller mass. So here if you see the smaller mass, it is very small so that you can't even see it, right? So then in that case, the optical branch, it becomes a flat line parallel to this k-axis, and this acoustical branch, it coincides with the k-axis. Now the vibrations of the acoustical branch, they can be excited by a force which makes the atoms in a crystal move in the same direction. So we need a force which can drive these neighboring atoms in the same direction. So this kind of effect may be produced, for example, by directing a beam of sound waves on the surface of a crystal. So these vibrations are therefore known as the acoustical branch. So because they can be excited by a sound wave, while the vibrations of the optical branch, they can be excited by a force which makes the two neighboring atoms move in the opposite directions. So the optical radiations induces this kind of vibration in a crystal. Hence these vibrations are known as optical vibrations. So what we need to get these two kind of modes or two kind of vibrations in a crystal is that there should be two atoms per unit primitive cell. Then only this type of behavior can be seen. Okay, so this is it for the lattice vibration in the case of diatomic lattice, and we have seen the lattice vibration theory. And to close this, I will tell you the significance of this lattice vibration theory. So this theory indicates the existence of frequency bands, so that is optical and acoustical bands in the diatomic and polyatomic lattice also. And these bands, they are separated from one another by a forbidden band gap, which depends on the ratio of the masses of the two atoms, the neighboring atoms. And this crystal cannot propagate vibrations of all possible frequencies. So there is a forbidden band gap for that. So only those frequencies are allowed which lie in the allowed bands. So that is optical or acoustical bands. So this is it for the vibration theory. We will meet next time with some other interesting topics. Thank you for watching this video.